This video covers a lesson found in Unit 7 on rational functions. The actual lesson itself is named Ratey, and it is quite a large lesson, and it covers 3 days in the curriculum. Now, as far as what Ratey is, it is an acronym that leads you through finding all the essential elements of rational functions in order to sketch a graph without ever having to use a table or a graphing calculator. The R stands for roots, which are zeros. Another term for that is X-intercepts. It also stands for removable discontinuities, which are your holes in the graph. Now, the very first thing you're going to want to do is factor the numerator and denominator, and they actually say that above here, where to make this tool effective, you want to factor the numerator and denominator completely. Then, anything that cancels out become holes at those x values, and anything left on top you set equal to 0, and that will give you your roots or your zeros or your x-intercepts. Now, to find the y-coordinate of the hole, that's where you take the factor that canceled out, you take the x value that would have made it 0, plug it back into what's left, the simplified function, and that will give you the y-coordinate of the hole. Now that we've factored set the top equal to 0 to find our roots, we can now move to the second part, which is the A, and that stands for asymptotes, which are, we're talking about the vertical asymptotes here. This is where you will take the denominator and set it equal to 0 and solve to see what makes it undefined. Now, when you get to T in Ratey, it stands for two things, it says. And what you're going to be looking for is you're going to be looking for even exponents on the factors. Make sure you realize that is on the factored version, not the original version. So it's almost like the multiplicity that the students learn in previous math courses. The T either stands for tangency, and it happens when this even power is in the numerator, which comes from the roots. And tangency just means it bounces off the x-axis. Kind of like when you have a double root for a parabola where the vertex is sitting on the x-axis, and so it bounces off the x-axis. Now, if the denominator has an even power on one of its factors, you have something called togetherness about the asymptote. Because again, down bottom, those factors give away asymptotes. And so if one of those has an even exponent, then you have what's called togetherness about that asymptote. And that simply means if you have a VA and it's going down on one side of the VA, then that means it's got to be going down on the other side of the VA as well. That's what togetherness means. And again, tangency means if this is the root, if it's coming down, it's going to bounce off and go back up. Now the E. The E stands for in behavior. And this is where you're going to either use your HA rules to find your horizontal asymptotes, or you're going to have to use long division to find your slant asymptotes. In this lesson, the A don't get any bigger than slant asymptotes, so you don't have to deal with any other polynomial asymptotes. Something that Ratey does not have them find is the points of intersection. So I will typically tell my students to also find the points of intersection as well. That's where if they have an HA, they would take the function, set it equal to the HA, and solve for x to see if they can solve for x. If they have to use long division, they can set the remainder equal to 0 and see if there's any points of intersection that way. And then finally, we have y for the Y-intercept. And that's where you just plug in a 0 for all the x's and solve for y. And when you do that, that will give you all the information that you actually need to be able to graph these rational functions. Let's look at an example of one. Let's do actually problem number 1. When we do problem number 1, we look at the function first, and if there's any factoring to do, we need to factor it. Well, there is no more factoring to do to x minus 4 over x plus 2, so we're ready to start with our Ratey. If anything canceled, we would cancel that out, and that would give us a hole in the graph, but nothing cancels out, so we don't have any removable discontinuities or holes. But we do have this x minus 4 on top, so that means we're going to have an x-intercept at what makes this the top 0, which would be 4. So we can actually go ahead and put that on our graph. Now, A, that's the vertical asymptote, so that's where you'd set the bottom equal to 0. And if we set x plus 2 equal to 0, that means we're going to have a VA at x equals negative 2. So over here we would have a VA at negative 2. Now, for the t, this is where you're going to look for even exponents in the numerator and the denominator on any factors. Since we don't have any, we're simply going to put none. You could put NA or something like that if you would like. E, in behavior asymptote. This is where you use your HA rules. So since if you look, these are the same power, so you're going to use the ratio of the coefficients. So we have an HA at y equals 1. We also want to see if the function intersects this HA anywhere, so I'll set the original function equal to 1 and try solving for it. Multiply both sides by x plus 2, leaves you with x minus 4 equals x plus 2. And if you try moving one of the x's, they both cancel out. And that leaves you with negative 4 equals 2, so there are no points of intersection. Then we can move on to the last part of Ratey, which is the Y-intercept. Just by plugging in 0 for all the x's, you'll get negative 4 over 2, which is negative 2. So the Y-intercept is negative 2. And now we're ready to graph the function. And I know this is a lot less points than what you're typically used to using when you do these, but again, we're just sketching the graph. Because we have these 2 points here on the graph, and we have these asymptotes, and I know I don't hit my horizontal asymptote, what I know is I know this piece of the graph looks like this. It's going to get closer to the VA, going down to negative infinity. It's going to get closer to the HA of 1. It's not going to touch it. Now, I know there has to be a left side of this on the left side of the vertical asymptote. So where is it? This is where you use the fact that there was no togetherness. No togetherness means if on the right side the graph is heading towards negative infinity, that means on the left side it's got to be heading towards positive infinity. And since it's heading towards positive infinity, it's got to be above that horizontal asymptote since you cannot touch it. And so that means out to the left it will keep on getting closer and closer to it. And so that is the sketch of the graph. Now, let's say, for instance, that the original function had a factor of x plus 2 that was squared. That would mean we would have togetherness. At x equals the negative 2. Which would have meant that the graph, the left side of the graph, would have looked like this, as opposed to being above. So the right side would still look like this. It's just the left side would now be also below the horizontal asymptote. All right, let's look at another one of these problems. Let's look at number 2. Number 2 is also factored completely for us. There's nothing for us to do, so we can go right into our Ratey. So R, nothing cancels out, so we don't have any removable discontinuities. But I do have a couple of factors on top that if I set equal to 0, I want to have x-intercepts at -1 and at 3. So we can go ahead and over here on the graph and mark those. A stands for the asymptotes. We have an x plus 2 down bottom, so that means we have a VA at x equals -2. Tangency, or togetherness, since we don't have any even powers, that means we don't have any. So again, this will be none. Now, E, in behavior. If you look at the top here, this has 2 factors. I'm actually going to erase that. But if you look at this, this gives us x squared on top, and we have an x down bottom. So that means this thing is top-heavy, which means if I'm wanting to find my in-behavior asymptote, I'm going to have to do some long division. So that means I'm going to have to divide x plus 2 into the numerator, and when I multiply that out, that's going to give me x squared minus 2x minus 3. And so if we do the division, x goes into x squared, x times, multiply, you get x squared plus 2x. And this is where I tell my kids a little rhyme to help them remember how to do long division. This is where you draw a line and change the signs. Those will cancel out. That leaves you with -4x. Bring down the next term, you get -3. And then x goes into -4x, -4 times. So that'll be -4x minus 8. Draw your line, change your signs. Those cancel out, and you're left with 5. If you wanted to see if it intersected, you would just set the remainder equal to 0, but there's no way that happens, so it does not intersect its asymptote. So that means for the end behavior, we have a slant asymptote at y equals x minus 4. And then for the y part, that's where we plug in a 0 for all the x's, so that'll be 1 times a -3 times a 2. So this will be -1.5, or -1.5. And so we have slant asymptote. We can go ahead and put our y-intercept. That's easier. And our slant asymptote is y equals x minus 4. So that means our intercept is at 4, and the slope is 1. So it's going to look something like that. And then I'm going to extend the vertical asymptote as well. Now, since I have roots at -1 and at +3, and then I have a y-intercept at -1.5, I know this piece of the graph looks like this. It's coming down, hits that point, hits the Y-intercept, then goes back up and approaches this slant asymptote. I know it can't touch the vertical asymptote, and I know it can't touch the slant asymptote because we just saw that it did not intersect it anywhere. Now again, if we had tangency, remember that would mean it would bounce off one of the roots. But since we didn't have tangency, it went straight through the x-axis twice at -1 and at +3. Now because we don't have togetherness, that means the other side, the left side, the graph has to be going down towards -infinity. It cannot be going the same direction as the right side, which is going up towards +infinity. So, and because we can't touch that slant asymptote, it looks something like this. And that would be how you would sketch that graph. So you can see how you can get a good sketch of these graphs without ever having to use a table or a graphing calculator, just by using this Ratey graphing organizer. Now let's go near the end of the lesson where you will see more complicated problems. Starting with number 12, they start doing transformations on these rational functions, like putting absolute values around the rational function, and they want the students to describe what that does to the graph. Number 13 as well asks for the changes in the domain and how the graph is affected by putting a square root over the whole rational function. And then when you get to 14, they start throwing in the more transcendental functions within the rational functions and ask for the changes there and also for you to sketch the graph. You can see number 15 and 16 involve trig functions within the rational functions. And again, you would just apply Ratey to be able to graph the functions. Again, 12 through 16 are more advanced type of problems. So you have the choice as to whether or not to cover these and in what depth with your students.